In section 9.4, we're going to look at testing a claim between two samples and their means, but these samples will be dependent. So we'll talk about what that means here now. So let's look at the definition. We say two samples are dependent if the sample values are paired. Each pair of sample values consists of two measurements from the same subject, or they are matched based on some inherent relationship. So let's look at a couple examples then. Suppose we measured the blood pressure of 40 randomly selected male-female partners and compared the group of men to the group of women. Now this is a dependent sample because we would take one set of partners and we'd have their blood pressure that would be, in a sense, grouped together. So these data are matched based on that inherent relationship of the male-female partnership. Now suppose we wanted to measure the weights of 20 randomly selected students at the beginning of freshman year and then measure the same group of students at the end of senior year and getting their weight. So this is dependent because we're measuring from the same subject just at different times. So in that way, the data from the beginning of freshman year to the end of senior year is paired, and so they are dependent samples. Let's take a look at the tools for testing a claim involving two means from dependent samples. The test statistic for two means from dependent samples involves a couple symbols we haven't looked at: D bar, mu D, and SD. So let's take a look at what those are. D bar is the mean difference of the differences of each pair of data. So in other words, we pair up the data, we find the difference of each of those pairs, and then from all those differences we calculate the mean, and that'll be our D bar. Mu D is the population difference of means, and SD is the standard deviation from all of the differences from our sample. Our null hypothesis is always going to be that the mean difference of the population is 0. So our test statistic becomes just D bar over SD, which is divided by the square root of our sample size. So let's try this in an example. Listed below are systolic blood pressure measurements taken from the right and left arms of the same person. So use a 0.05 significance level to test for a difference between the measurements from the two arms. So notice that our claim is that there is a difference between the measurements from the two arms. So if you look at our data, each column represents one person, and we took the measurement in their right arm and then the measurement in their left arm. We did this for 5 people. So our claim is that there is some difference between those measurements, which means that the population difference does not equal 0. There is some mean difference between the right arm and the left arm measurements. Then the opposite is that mu D equals 0. From there we get our null hypothesis and alternative hypothesis, just as we've done before. This tells us that we're dealing with a two-tailed test. Of course, our significance level is 0.05. Step 5 then is to calculate the test statistic. But in order to calculate the test statistic, I need to figure out what all the differences are of my sample data. So I've got that here now in my third row. I simply subtracted the bottom number minus the top number for each pair of data. So then I need D bar, which is the mean of each of these differences. So we have to calculate the average or the mean of these 5 differences, which I get to be 72.2. That is, we simply add up the differences and we'll divide by 5, gets us 72.2. So we also need the standard deviation of these differences. Of course, we've been using Excel to calculate this, but you may also use your calculator using the standard deviation for a sample formula. I find that the sample standard deviation of differences is 9.31. So now, using my sample size of 5, I can plug all this into my test statistic, which gets me a test statistic of negative 17.33. So let's find the p-value with the student t-distribution table, but of course, with the t-distribution, we are not finding the exact p-value, we're just finding whether or not the p-value is less than or greater than a certain number. And in particular, we eventually want to know if the p-value is less than or greater than our significance. So on our t-distribution, our sample size was 5, so that means we have a degrees of freedom 4. And my test statistic was negative 17.33, but of course, for the t-distribution, I consider the positive version of that test statistic, which is greater than the furthest number to the left. So that means my p-value should be somewhere over here, but of course, since we're in two tails, I gotta be in this second row. And so if you look at the trend of my my probabilities, that means my p-value has to be less than 0.01. So we found the p-value to be less than 0.01. Since that is less than the significance level of 0.05, we can reject the null hypothesis. Since the null hypothesis was that the mean population difference was 0, which we rejected, there does not appear to be enough evidence to suggest there is a difference between measuring the left arm versus measuring the right arm.